All right, let's get started with the day. And I'm just putting this up here because that's, I think, one of the important things that we as faculty can do for you all is to identify opportunities for you where people are looking to hire folks. And this company, it used to be just Power Engineers, now it's WSP, a member, it's Power Engineers, but a member of WSP. But they're going to be on campus today, 4 to 5. And they are a huge company. The power side of it, I don't know how much it has, but it has quite a few folks. And the two gentlemen that will be coming up are alum from this particular program, former students of mine. So it's only going to be an hour. It's going to be in the Hill Auditorium, which is in the new part of Barrows at the end. If you know what that is. So literally you walk out of our classroom, you go down the steps, and then you just kind of keep walking straight until you run into the door. There's 2 doors on either side. There's a little conference room sort of in the middle, but you have to go in the doors outside. And they're going to have free food, right? You're going to have a little bit of a catch. But yeah, it's a really good company. Luke, you interned there, right? You did. That's right. You were supposed to be the selling point stuff. So I don't know. Do you want to talk a little bit about it for a couple of minutes about working for that guy, Adam? We won't say too much negative stuff about him. Maybe we'll do that off camera. No, I like Adam a lot. He's a really good guy. And Jordan too. So go ahead.
Yeah, I worked with Adam and I got the Hallwell, but a bunch of good guys, and it's a good environment to be in. Anytime I had a question, like I could easily approach anybody in there and they're willing to help. Yeah, I mean,
Well, they're smart guys, right?
Oh, definitely.
Both really smart, very different. Jordan does more of the computer side of things, like setting up networks that work in the utility system, where Adam used to be, it says substation engineer, but he's more of a manager now, right? I mean, he's pretty high up.
Yeah,
He does engineering design, but he does a lot of management stuff too, was the last time I talked to him about it. So, but just a really good guy, very calm. You like a supervisor who's not going to be animated and yelling and screaming and all that stuff. So yeah, he's a really, really good guy. And a little bit of background about the Hollowell, maybe Braden doesn't even know, but the Hollowell office didn't exist until probably about 4 years ago, maybe 5 years ago. And it started because another company in Augusta had gone through some changes in terms of how they ran their business. And so some of the key personnel, including Adam, actually left and started the Hollowell office for power, because their main office, MAINE office, is actually in Freeport. But I think more people now work in Hollowell than actually do in Freeport. And Hollowell, if you don't know the area, it's a quaint little downtown. It's got a lot of things. I think it's in an old theater building, right? The office, but they've since modified and added on. So now it probably doesn't look anything like a theater building, but they do really good work and they're well respected. Adam's talked about projects he's done in Houston. So he's done presentations in the past and just done some really cool work. So, a lot of it is just having a good feel for the work we do, but working with really good people really, really helps, in my opinion. So encourage you to check it out. Just like SGC a week or 2 ago, we get another really solid company to get a peek on, and they're going to be at the job fair tomorrow. I'm pretty sure that's why they're having it today from 4 to 5. And they'll actually be at the job fair. And again, if you want to get, a good representation, if you go to the opportunity the evening before, where they're not going to have quite as many people, right? Like the job fair is going to be at 5,000 people. It's going to be crazy. And they're going to be dealing with 5,000 people during the course of the day. It's a lot for them. It's a lot for everybody. So going there might be 50 people, maybe 40 people. So you have a lot more of a personal interaction with them. And then you can get business cards. And then if you go check out their booth the next day, I remember you. Remember I talked about this. And so that gives you a leg up. So when you're looking for internships and whatnot, that's a little bit of stuff to do. So this is going a little bit above and beyond. But anytime you can do a little bit above and beyond, it just distinguishes you. So just give you a personal example. This just happened yesterday. So I have a 5th grader. My son is a 5th grader. He's one of the youngest 5th graders because his birthday is in September. And he's, reasonably tall for his age, but not skyrocketing tall. But he tried out for a basketball team for the 5-6 Bangor basketball team. And he's the only 5th grader that made it to made it under the 5-6A team, but a high quality team, whatever. And the person was asking me, like, why do you think he made the team? It's like, because he works his tail off. He was there, he was shooting in the morning. So he put the extra time in not because he's tall, not because he has freak athletics. Just look at me, right? You're not going to get freak athletics from me. But the idea is that you just put, he put his time and he puts his best foot forward. And as a result, the impression of him is this is a good kid who works really hard. That's what you all want. You want to give that impression. So little things that don't take a lot of time, like if you get class from 4 to 5, obviously don't skip your class. But if you're just going to be home, hanging out, playing PS5, you may want to make a better decision because you can still play PS5. You might just do it after the opportunity. And I know like Luke, I thought he was a power guy, but it's not even about like having a competition. It's just like learning different companies and different people. And you never know what the network will happen. People might want to, hire you. People might want to partner with you in your company. And it's just a good network to set up. So it's a really, really, really good idea. And then you can also go and harass some of the upperclassmen. I'm pretty sure if Noah and Wyatt had better be there. I think that they were supposed to be there, but I know you're supposed to be there because they already gave you work.
Yeah.
We saw some emails and like, Braden, do this. It's like, I wanted to say, by the way, is he getting paid for this? And if they would have said yes, then what about me? Am I getting paid? Because I'm happy to actually do it because they're really good guys. So again, good, solid company, worth checking a look. And you don't even have to go out in the rain. You just hang in the building, you can just walk down the street. And now we have heat. I called to complain because there was no heat in my office this morning. It's like, we need heat at some point. It's like 50 degrees in my office. So please give me heat. Anyway, you can tell I'm fired up. I've been up for a long time and I did a 30-minute run this morning, only in my basement because it was kind of cold and rainy, but. All right, so there was a homework question. Correct?
Yes.
Last problem, this is homework number 3.
So my question is almost a bit as easy as it sounds sort of deal. So like just put together a mesh equation for that, but do we need to have that in terms of time constants?
Yeah, so you're going to write it in the time domain. So you're going to have LDIDT and CDVDT, right? And I've given you some initial conditions there. So I just want the mesh equations. That's it. You don't have to solve for it because you really can't, right? This is not a first order circuit. This is a second order circuit. So you would not be able to solve this circuit unless you had taken the class in different complete. Most of you all haven't. So that's all. Okay, good question. All right. What
Hey,
is
Paul.
Yes.
I think Arthur had a question in the chat.
Oh, Arthur, go ahead. What's your question?
Oh, I put it in the chat, but yeah, I don't think it really matters because I can carry it through, but I was just wondering if there was an initial voltage at t less than -1 on problem 1.
For which element?
Is there an initial voltage across that capacitor before it instantaneously starts taking a current at?
Well, you do
equals-
know the initial condition of the voltage, right? It's 12 volts, right? So remember the voltage.
No. Problem number 1.
Oh, problem number 1. I'm sorry. Yes, there has to be, right? Because it's being charged.
Mhm.
So there has to be an initial condition, right? Just before time 0, which is the initial condition, but previous to -1, there's no initial voltage.
All right, so we can assume that the voltage across it is 0 at t equals -1.
Correct. Yep.
Okay.
Good question. Thank you. So S it's a really interesting thing, but it is a variable. And it is actually, we're going to call it the complex representation of frequency. And sounds kind of weird, right? When you say complex representation, it's not complex as in hard. It just means it has a complex number. So let's see if it works for all frequencies, including DC, right? DC is a frequency, just happens to be 0. So we'll go back to Euler's identity, m e to the j theta, right, equals m times cosine of omega t plus j sine of omega t. And theta is equal to omega t, right? We know that that's where we have an actual radiant frequency because we have a waveform. We don't have a fixed number. So if we plug in DC, which means our frequency is 0, Then our J theta term or a theta term, right, becomes omega times T, and omega is equal to 0. So 0 hertz is 0 radians per second. 0 times T is still equal to 0. So m e to the j0 is just m times the cosine of 0t plus j sine of 0t. Well, the cosine of 0 is 1, right? Cosine of sine is 0. So that just becomes m. It doesn't vary. It is a constant value whose magnitude is whatever you want it to be. Could be 12 volts, could be 250 volts, it doesn't matter. So we just checked that, yes, that using our variable S as a DC input, a frequency of 0, is going to allow us to go ahead and we can represent that correctly. How about any old sine wave, 30 hertz, 40 hertz, million hertz, it doesn't matter. Well, if you remember from the previous class where we did a bunch of work to derive the sine of omega t, the Laplace transform of that, we proved that the sine of theta is e to the j theta minus e to the minus j theta over 2j. So if we plug in a frequency here, let's call it 30 radians per second, then this is going to be 30 times t, right? Which is going to give us a varying number. So again, we can go ahead and represent any sine wave, any frequency sine wave with that value, or we can do a cosine wave, right? We can go ahead and represent it as a cosine wave. And finally, we can introduce any sine or cosine with a phase shift and get it to accurately be represented with there. So we'll say that S is equal to A plus J times B. So A is going to take care of the real part, and B is going to take care of the frequency. So A is the decaying exponential term, if there is a decaying exponential, and B is the actual frequency term. And we'll actually see more and more how we look at Laplace that we'll see that B term used more extensively. A and B can be 0. They can both be 0. At DC, S is equal to a big fat 0. So now we've got the definition of Laplace, and now we actually will present a table. Because once you get through the grind of deriving your Laplace transforms for all your variables, then it just becomes look it up in the table. So you can see here, we have a function in the time domain. That's called f of t. And there's an equivalent or transform function in the Laplace domain called f of s. And so you can see an impulse function, which is the Dirac delta function. That's the letter delta, or one of the letter deltas. That Dirac delta function of t is just equal to 1 in the Laplace domain. The unit step input, right, which is just u of t, that we derived last week as 1 over s. A unit ramp, right, so t, 1 over x squared. T to the n, whatever value that's going to be, n factorial over s to the n plus 1. Do y'all remember what n factorial means or what the factorial operator means? You can say no, it won't hurt my feelings. It's not one you use a lot. So in math terms, when you see the exclamation point, that just means factorial. So let's say this is 3 factorial, okay? 3 to the exclamation point. If you wanted to write that out and actually the mathematical operations you're supposed to do, 3 times 2 times 1. 5 factorial, 5 times 4 times 3 times 2 times 1. Get the idea? You're just multiplying all the way from 1 to whatever the integer is, and you're going to end up with there. And I've only ever seen factorials used with integer numbers. I've never seen it with decimals. So I can't categorically state with 100% certainty that you can use it for, or you can't use it for non-integer numbers, but I believe you can only use it for integer numbers, but you can check with the math department on that. So That again, if you have t to the n, it's just n factorial over s to the n plus 1. E to the minus alpha t, we derived that one last week. That's 1 over s plus a in the Laplace domain. T times e to the minus alpha t is 1 over s plus a squared. And then we start getting into our sine and cosines. And this is only for time greater than 0. Again, this is when we're going to have our unilateral function. So Windows calculator, you use n as a decimal. Oh, okay, maybe you can use decimal. I've never seen it as a decimal, so thank you for checking that out. But the sine of omega t, omega over s squared plus omega squared. The cosine of omega t, s over s squared plus omega squared. The e to the minus at, sine of omega t, you can see is omega over s plus alpha squared plus omega squared. And then the cosine times e to the minus t is s plus a. I will highlight the most important ones that you will use. That one you'll use a lot. That one you'll use a lot. This one and that one. We almost never use cosines because we have this variable s plus a in the numerator or s in the numerator, and that's a lot harder to add in. So when we do something called partial fraction expansion, we'll always use the sine expression, the sine of omega t or e to the minus alpha sine of omega t. So here's a nice thing. Remember, engineers, we like to be efficient. So we don't have to derive this table. Once we've gone through the process of deriving them, we're just going to take advantage of the fact that this is just a table. So we can look it up in the table. So as long as you make your functions in the Laplace domain look like they do in the table, f of s, you can go back into the time domain just by using the table. And unless I tell you otherwise during a test, you can use the tables. You can just go ahead and use the table and look it up. Because again, that's what everybody does. So once we have this table, now we can take the table and we can convert our time domain functions from the time domain into the Laplace domain. Hey, can you shut the door? We can shut the door. We can go ahead and convert time domain functions into the Laplace domain. Then we can do whatever work we need to do in the Laplace domain, come up with a solution, and then we bring that back into the time domain. Okay, so it's kind of a circular process to how we do it. And again, why do we have to convert into the Laplace domain in the first case? Because we have real world systems that are modeled with differential equations. And we don't want to solve those differential equations using math techniques. We want to use Laplace techniques to make it really, really easy for us. And here's that process. We start out right here. We write a linear differential equation, okay? If you're really good at math, then go and get your solution, because we live in the time domain. We want an answer in the time domain. So good at math, go right into the time domain. But we may or may not be good at math, and it's actually easier. So the step we're going to do is we're going to go here. We're going to go to the Laplace domain. And we're going to analyze our system in the Laplace domain. Then we're going to solve that equation, or equations plural, using just standard algebra. Once we have done our algebra, now we actually have a solution that's in the Laplace domain. We know what the answer needs to be, but the problem is it's in the Laplace domain. So we want to be in the time domain, so we do our inverse Laplace transform, and then we end up back in the time domain of the solution. Okay? So it's a kind of a little bit of a longer process from it appears, but this right here, you have to solve with differential equations. All right? So going into the Laplace, the whole purpose is so that you don't have to do differential equations. You don't need to solve for it. And it works perfectly fine. So we're going to transform any, and you notice it's reasonable, right? A reasonable input is a DC, is a sine wave, could be a ramp, could be a decaying exponential. It's probably not going to be an exponentially increasing system, right? Because at some point, it's just going to keep going to infinity. So you can't go to the store and buy a power supply that represents an increasing exponential, because after 50 years, the output's going to be millions and millions and millions of volts. It's not practical. So we're going to use reasonable inputs and a system model, and the system model can be whatever you need it to be. And we're going to go from the time domain to the Laplace domain. We've already analyzed those reasonable inputs, constant, which is DC, sinusoidal, or decaying exponential. Now we're going to go ahead and we're going to go and analyze the system using algebra. Plus, minus, multiply, divide. We are not going to do integral and derivative in the Laplace domain. But if you're in the time domain, you have to do all those different functions, all those mathematical functions, plus, minus, multiply, divide, derivative, and integral. And you could be doing multiple integrals or multiple derivatives. So what we want to do is, to take advantage of Laplace, we want to make sure that all these properties in the time domain, so these are in the time domain, multiply, divide, add, subtract, integral, and derivative, what do they look like in the Laplace domain? So all those mathematical properties in the time domain, we have to convert them and find out what the equivalents are in the Laplace domain. So, whoops, did I copy that page? There's a duplicate. Sorry about that. I have an extra slide in there. So let's just do the first one. Let's find out the mathematical property for adding signals together. We've got two input signals, F1 and F2. And we want to take the Laplace transform of those and see what the result is on the output. So we go ahead and set it up. We have the Laplace transform integral equation. And so we have f of t. So this whole thing here, right, is f of t. So that means this whole thing is f of t. So we're going to convolute that with this e to the minus st dt, and then we're going to integrate it from 0 to infinity. Well, when we set up our math, we can go ahead and distribute our e to the minus st dt's to both those functions. And if I look closely at those two integrals, isn't this just f1 of s? And isn't that f2 of s? If we individually applied f1, function f1, without having f2 anywhere near it, we just run it through the system, then we would get f1 of s. We'll do the same thing for f2, and we would get f2 of s. And then when we add those together to get the combined input, we just get those that way. So what did we say? Addition or subtraction in the time domain is exactly the same, okay? Is exactly the same as addition and subtraction in the Laplace. So if you are adding a bunch of F1, F2s, F3s, F4s, whatever in the Laplace domain, that's the same thing as adding F1s, F2s, F3s, F4s in the time domain. There's no difference. Okay, and that's a huge advantage to us because that allows us to use what we call partial fraction expansion. Now let's go ahead and do multiplication. So multiplication is, we're going to take those two different functions, f1 of t and f2 of t, and we're going to figure out what those would look like in the Laplace domain. So we'll run those through our converters. We have f1 of t, e to the minus st dt is just f1 of s. And the same thing for f2, we have f2 of s. Now, when we multiply those two functions in the time domain, are we going to get f1 of s times f2 of s? Well, we get this. Do those look the same? If I multiply them together in the time domain and then run them through the converter, do I get the same result as doing them individually and then multiply them together? The answer is no, right? Because you only have one e to the minus st dt here, right? Over here, when you multiply them together, you end up with 2 of those. Okay? So multiplication in the Laplace domain or in the time domain is not the same. If you multiply 2 functions in the time domain, it's not the same thing as multiplying in the Laplace domain. So what that means is if I get the Laplace of f1 of t times f2 of t, that does not equal f1 of s times f2 of s, which is kind of a drag in some respects, because if it was the same, it would make our world quite a bit easier. So what we need to do, this doesn't work for us, right? But we still want to look at our table, our Laplace table, and be able to go back into the time domain. Well, we can't use multiply. So if you remember back from maybe pre-calculus, if you can take f1 of t, well, let's do f1 of s, sorry. If you can take f1 of s and f2 of that s and convert those to f, we'll call it 3 of s, plus f4 of s, then you can go ahead and get those back into the Laplace, into the time domain using the tables. Because addition here in the Laplace domain is the same as addition in the time domain. So you can't multiply. You first have to take those multiplied functions, break them up into additions, and then you can go back and use the Laplace tables and get into the time domain. This, if you remember, do you all remember partial fraction expansion? Maybe. I think at UMaine, they do it in pre-calc, MAT 122. Okay. Well, essentially what partial fraction expansion is, if I have S plus A over S plus B, and we have C, that's going to be equal to D over S plus A plus E over S plus B. Partial fraction expansion allows us to solve for the D and the E coefficients so that you get back your original, multiplied functions. That's partial fraction expansion. And we'll show you how to do partial fraction expansion. The way I recommend to do it might be a little bit different if you were taught how to do partial fraction expansion in the past, but we'll help make sense of that. But this is a key thing, because multiplication in the time domain is not the same as multiplication in the Laplace domain. We've got to do partial fraction expansion. That's the hardest part about Laplace, is making your functions so that you can look it up in the Laplace table and you can bring it back into the time domain. And most of the functions we'll have to deal with, you're multiplying 2 functions in the Laplace domain before you can bring them back into the time domain. Okay? What about time integration? So I'm integrating a function, right? So if you're not sure what I'm asking for, here's a function, and I'm going to do a mathematical property where I'm going to integrate that function, right? Like in the case of a capacitor, right? The voltage in the capacitor is integrating the amount of current going into the capacitor, right? Charges it up. So if I run a current into that capacitor, I can actually measure or calculate what the voltage is. And I do that by using the integral. So I've got to be able to do integrals in the time domain, and I want to see what they are in the Laplace domain. So here's my function. And again, I'm starting at 0 because it's only unilateral. I go from 0 to infinity, f of t dt. I'm going to put that into my Laplace conversion, which is the 0 to infinity, f of t, e to the minus sttd. So all I do is I substitute this whole thing in for, I said f of x, not f of t. And the reason why I want to change the variable from x and not to t is because then I would end up with a bunch of t variables, right? So it gets confusing. So I'm just gonna call and integrate that with respect to X, just so that I can actually differentiate between the two. And that's the definition of f of s. So do you remember integration by parts? Do you all remember that? Calc 2, been a minute. Anybody remember integration by parts? So integration of u dv is equal to v du evaluated at the limits, and then minus, or is it plus? This is v du, gonna show that, plus, why am I not forgetting? I have it on the next page. It's, I think it's just udv. Integration by parts.
I feel like I did it. U times v plus the integral of v du.
Well, let's see. I have it here, right? So I have u, we're going to define as e to the minus st dt. That's our s e to the minus st. Du, so this here, it's u, and then it's u times, it's u dv. It's got to be u dv, right? Here, why am I? I'll just bring it up. I'll just bring it up with Edge. I've done enough of these, you think I'd remember them, but this is the thing about calculus. You don't do it all the time. There we go.
Yeah,
So the integral of u dv is equal to uv minus the integral of v du. So let's go back here and change it. Try to make that a little cleaner. So the integral of u dv is equal to uv minus, and this is evaluate the limits, minus v du. All right, if you remember integration by parts. So what you want to do is you want to go ahead and you want to basically integrate by parts so you can get one of the t or one of the expressions sort of so that it doesn't have any t terms associated with it. So if you notice that I picked u equal to the integral part of f of x dx, and so du is just going to be f of t dt. And then my v, or my dv, is e to the minus st dt. So my v is just equal to minus 1 over s e to the minus st. So if I plug in into this formula here, what I end up with is 1 over s. Well, did I evaluate it out of the way? I think let's do the uv evaluation here. So uv is equal to the integral f of x dx, and then v is minus 1 over s e to the minus st, and that is evaluated from 0 to 0 to infinity here. And what ends up happening is when I evaluate the limits here, e to the minus st becomes 0, right? So this becomes 0 minus 1 over s times the integral of f of x dx e to the minus st dt, right? That's my function. Well, if you look over here, this function over here, actually, it's not the dx, it's, I think I got an extra dt in here. So that function, f of x e to the minus st, is just f of s, isn't it? It's just the f of s expression. So when I look at this in more detail, this function over here is the definition of the Laplace transform. And all I've done is multiplied it by 1 over s. Notice that I can move the 1 over s in front of the integral. And the reason why I can do that is because I'm integrating with respect to t. So s is a constant. It's not changing. So I can move that out front of the integral, and what I end up with is just 1 over s times f of s. So integration in the time domain is equivalent to dividing the Laplace transformed function that you have, your f of t, you convert that to the Laplace domain, and you divide it by s. That's huge, right? Because instead of actually having to integrate, I just divide by s. I don't have to do any integration part. I'm just dividing by s. So again, that means that I can use algebra to go ahead and solve for that. All right. So integration is just dividing the function by s. Now that's why I must have skipped a page. So that's why it was confusing me here. Let's do the same thing now, but we're going to do differentiation, because in the time domain, we only have 2 cases that we have to use differential equations. We do integrals or we do derivatives. We've already done integrals. Now we're going to go ahead and do derivatives. So we're going to take the Laplace transform of the first derivative of any time domain function. So I'm going to plug that in here. And that is my expression that I'm going to have to do. Again, I've got to integrate by parts because I want to make it so that I don't have this, this wacky t situation, because there's nothing I can do to the e to the minus st to deal with it. So I want to get rid of the derivative function over here. So my u is e to the minus st. My du is just, I'm going to go ahead and take the derivative of that. So that becomes s e to the minus st. Then I'm going to take my dv, which is the rest. So that's this part here, and I'll put rectangles around it. And when I integrate the derivative of f of t, a dv, then we just have v equals f of t. Okay? I get an extra term there, so it should just be that term there. I don't have an equals. So now I'm going to plug those in and evaluate, and what I got is f of t e to the minus st evaluated from 0 to infinity minus f of t times minus se, and here, let me just clean this up because I've got a couple typos on this slide. I forgot the minus sign right here. That needs a minus, and this term, that has to go away. All right. Let's try that again. Save it. Wait for the hamsters to stop running. Zoom uses a lot of resources. The computer is going to melt down. You can hear the fan running for so long. Opening a document. Why is it opening a document? Did it close the document? Come on. No, it's good. Okay. That was weird. So now I'm looking at it and I see that my derivative of the Laplace domain conversion of a time domain derivative becomes f of t e to the minus st evaluated from 0 to infinity minus 0 to infinity f of t minus s e to the minus st. So again, I'm going to move the minus sc and I'm going to move it out front over here. So what I'm left with is s times f of t e to the minus st. This right here is the definition of f of s, right? That is my actual f of s, Laplace definition. But I also have, when I evaluate the limits over here, I can see that I have 0 and I minus function f of 0. F of 0 here is the time domain initial condition. Notice this is a capital F over here. It means it's the Laplace transform function, the time domain transform function. I end up with an f of s. Over here, that is a lowercase f, which means that that is its time domain initial condition. So doing the derivative is multiplying by s and then subtracting any initial conditions. Okay, so we've just taken care of our two equations that we would have to do is to solve. We'd have to use differential equations to solve for it. We don't have to do integrals. That's multiply. I mean, that's divide by s. And we don't have to do derivatives because that's multiply by s. So here's our table. These are all of the mathematical properties that makes things hopefully pretty easy for us. You can see if I do something with called time shifting, which I don't start something at time 0, I started at 1 second. I have this e to the minus t naught s times f of s. So I don't have to do any special integration. I could just multiply it by e to the minus t naught, which again, that is the delay that's associated with it. If I have a unit step that is, the unit step is delayed, then I have a little more work to do. I still have to do the Laplace here, but that one we'll never have to worry about. If I have e to the minus at alpha, then I can just plug in f s plus alpha. So anytime I see s in my table, I just plug in s plus a. If I take the highest order derivative, n, I multiply by s to the n, and then I just subtract initial conditions. You can see over here, this is the actual expression, its initial condition. This is the initial condition of the first derivative. This is the initial condition of whatever derivative you have to go up to. If I multiply by t, then I have to do derivatives. Again, you're not going to have to worry about that one. And this last one is I'm just integrating a function over time. So again, the ones that I really need to highlight, that one and that one. Those are the two that I need the most. Okay, that's the whole purpose of Laplace. Let's do another mathematical property, and this one we'll use a lot, especially next semester. It's called the initial value theorem. Wouldn't it be great if I had a way of figuring out a time domain output or time domain value given a Laplace domain function? That's what the initial value theorem does. So if I'm looking for the initial condition, I'm going to multiply my function in the Laplace domain, the converted function in the Laplace domain by s, and take the limit allowing s to approach infinity. And that will give me my initial condition. Okay? So again, really helpful because I don't have to get the solution, bring it back to the time domain and do partial fraction expansion. I can just go ahead and grab the information I need simply by doing this initial value theorem. So let's take a look at a simple example. So we have an f of s, which is equal to s plus 2 over s plus 1 squared plus 5 squared. And I want to go ahead and figure out what the initial condition of this one would be. So find f of 0. So I'm going to use my initial value theorem. And I'm going to take a limit as s f of s as s approaches infinity. So do you ever remember what you do when s approaches infinity? What happens? What do you end up doing? You basically take the s terms in the numerator and the denominator, they're the higher order s terms, and you sort of cancel everything out. So what you'll see is over here, I expanded it. So I do the limit. So I multiply s through, I get s squared plus 2s. And in the denominator, I have s squared plus 2s plus 1 plus 25. I'm dividing out the highest order s term. So I multiply that by 1 over s squared. I multiply that by 1 over s squared. Does everybody know why I did that? Let's write it out. So I have 1 plus 2 over s all over 1 plus 2 over s plus 1 over s squared plus 25 over S squared. Why did I go ahead and factor out the highest order S term? Because when the limit as S approaches infinity, what happens here when that goes to infinity? What happens to 2 over infinity? Goes to 0, right? So all those terms go to 0, and you end up with 1 over 1. That's how you do it, sort of a mathematically rigorous way to do it. Okay? Now, I would show you, well, actually, you know what? Let's do this. I'll show you how to do this the partial fraction way. Whiteboard still up? No, so I gotta do whiteboard. Let's clear the canvas. All right, so let's plot. What I'd like to do is we'll do this for practice, but I want to find f of 0 using the old fashioned way, which means I have to take this back into the time domain. So I'll show you how to do the time domain. First thing I need to do is go back here and look at the table. Is there any functions in here that look like this? That look like s plus 2 over s plus 1 squared plus 5 squared? Anything here? So you're looking in the f of s. Do you see anything that looks remotely like that? Anybody? Second to the last one? Close, but there's an S in the numerator, right? So the last one is the one that I have. So if you remember the last one, and I'll write this, this is the f of t for the last one. That says e to the minus alpha t cosine of omega t. The corresponding f of s is s plus alpha over s plus alpha squared plus omega squared. Are those the same? Can we just go ahead and plug those in? Well, here's the trick. If I look at the denominator terms and focus on that, I can always monkey around with the numerator a lot easier than I can with the denominator, right? So if I let alpha equal 1 and omega equal 5, what I can end up with is s plus 1 over s plus 1 squared plus 5 squared, right? And then it looks exactly like the table. There's a problem though. I have s plus 2 in the numerator, not s plus 1. So what do I need to do? Add a 1 to it. Isn't that the same thing? Just added 1. And now, using common denominator, what I end up with is s plus 1 over s plus 1 squared plus 5 squared plus 1 over s plus 1 squared plus 5 squared, right? And so this one over here, f of t, is equal to e to the minus alpha t sine of omega t if f of s is going to be equal to omega over s plus alpha squared plus omega squared, right? That's one of the table ones that we had. That's the table that Braden mentioned earlier. That's the number just above it. So do I have, again, looking at the denominator, do I have all the conditions that are met? What's missing? So I have alpha equal to 1 and omega equal to 5. So if I wanted it to be able to use a table, I need 5 over s plus 1 squared plus 5 squared, correct? Does that match what I have here? What do I do to make a match? How about I divide by 5? 1/5 times 5 is 1, isn't it? Isn't that what we originally had? So when I have this function over here, f of s, which is equal to s plus 2 over s plus 1 squared plus 5 squared, that's going to equal s plus 1 over s plus 1 squared plus 5 squared plus 1/5 5 over s plus 1 squared plus 5 squared. That is essentially partial fraction expansion, isn't it? So now I can look at my tables and then I can see f of t is going to be equal to e to the minus t cosine of 5t plus 1/5 e to the minus t sine 5t. Just use that, got it from the table. Now, I want to know what f of 0 equals. Question? No. Okay. So now I just plug in t equals 0 everywhere. E to the minus 0 cosine of 5 times 0 plus 1/5 e to the minus 0 sine of 5 times 0. What does that equal? I don't want to see anybody using their calculators.
E to the minus 0?
E to the minus 0, yeah, it's 0t, but t is equal to 0, yes. What does that equal? What is the sine of 5 times 0? You recall being punished? I'm not sure what minus is, but e to the 0 or minus 0 is 1, but the sine of 0 is 0, isn't it? And this term here is 1 and 1. So f of 0 is equal to 1. Isn't that what we did when we did the initial value theorem example? We came up with the exact same answer. Which one is easier? Using this theorem here, right? Using the initial value theorem, or doing all this work, and that work we had to do was to solve for f of t, and then we could plug in t equals 0 and then solve for the initial condition. That's what we did. So hopefully what you see, there's a lot of value to using or staying in the Laplace domain for as much as you can to simplify your work. Okay? Let's do the final value theorem. Final value theorem, limit s, f of s approaches 0, gives you the final value in the time domain. So the initial value had s approaching 0, infinity. The final value s approaches 0, but you still multiply by s, same exact thing. So let's do this one. S plus 2 squared minus 3 squared over s plus 2 squared plus 3 squared. We want to find f of infinity. So we're going to take a limit as s approaches 0, f of s. This one we're going to multiply our s term over here. And when you multiply your s term, what ends up happening? Well, the difference here is, again, you're looking for the highest order s term. In this case, they're both s squared, so those s terms are going to cancel out. And then you multiply something times 0, it's going to be equal to 0. So your final out value theorem for this particular one is 0. Five minutes. Go ahead and prove f of 0 is 0, doing the time domain approach. I'm only having you do that just for practice because it actually is going to help you with partial fraction expansion. So go ahead and do this one. I'll make it slightly easier for you. So you have that one, and then I'll also bring up the table that hopefully has, let's see, so we have, well, we don't actually have it on this table. We have it right here. So essentially, what we'll do is we'll have an f of t. That's going to be equal to t e to the minus alpha t times the cosine of omega t. The f of s equivalent there is going to be equal to, let's see, s plus alpha squared minus omega squared over s plus alpha squared minus or plus omega squared. I just want to make sure, is that correct? Let me just double check because I don't know if I have. Let me bring up Edge real quick. All right, let's see if we have that one in here. No, we don't want that one. That's the Laplace table. We don't want that one. That one's too basic. Let's see if this one has it. Oops, what happened? It just disappeared. I want the Laplace inputs, not the. Let's see if this one has it. No, this is Fourier, so we definitely don't want Fourier. Maybe we got to type in something more specific. Laplace transform table. See if they can do it that way. I think this is the one we want. That's t. Where's the decaying exponential one here? Well, I guess it's not in this table. It's probably more of a complicated one. So I'll just give you, this one. So I gave you f of t and f of s. Can you solve for that? Can you solve for find f of infinity? The final value theorem, not the initial, not the initial condition. I'll give you a couple more minutes. I've been yapping away. This took up some of your time. All right. This one's actually easier than it looks. Because I already gave you what that is equal to. So my f of t for this function is going to be equal to t e to the minus 2t cosine of 3t. So f of infinity, I'm going to plug in infinity everywhere for t. So this is infinity. This is e to the minus 2 times infinity times the cosine of 3 times infinity, right? So this is a tough one, but we know that this number here, that's going to vary between +1 and -1, right? It's never going to go higher or lower than positive or -1. So that one's pretty easy. The hard part is these two. One has to dominate over the other. Infinity times e to the minus 2 times infinity. Anytime you raise something to an exponential, especially if it's a number greater than 1, it's going to go to infinity or minus infinity faster than this number will here. So these two multiply out and equals 0 because the e to the minus 2 times infinity approaches 0 faster than the infinity term. And you can get a little bit confusing, but that's just a race. And it basically the e to the minus 2 wins. So this is 0, which matches what we had here. But again, you had to use the tables and make it look like something in the table to make it work, where over here, you just ended up doing the math. Okay? So hopefully easy peasy. Here are all the Laplace operators, the mathematical operators that we'll be doing. So you can see we have the definition of doing the Laplace transform. That's the very first one we have. We have the addition, which is linearity. So addition in the time domain is the same as addition in the Laplace domain. If we take the derivative of something in the time domain, we have s f of s minus its initial condition. And notice this technically is 0 minus, right? So not the 0 plus, but the 0 minus condition. So it's just before something has transition. If you have the second derivative, then you just have to go and do it just becomes s squared times f of s. So you have a couple of additional multiplications of s you have to do. If you go up to the nth derivative, then it just becomes s times n. So you multiply your function, your Laplace domain function by s, the number of derivatives you have to take, and then you subtract the initial conditions for each of the previous stages. Integration is division by s. Take the Laplace domain equivalent and divide by s. If you multiply by time, then you got to take the derivative. You probably will never have to do that. If we do a time shift, so we delay something, we just have to multiply by e to the minus whatever the time shift is times f. We're never going to have to worry about complex shifting, time scaling, and convolution integrals. Convolution integrals is more of a communications thing, so we don't have to do it. So I would really not worry about that one and that one. All the other properties are pretty helpful or pretty useful to us. The only property we didn't cover is if I take the Laplace domain of k times f of t, where k is a constant, right? It's 5, it's 17, whatever. What does that look like? Well, that becomes the integral from 0 to infinity k f of t e to the minus st dt, right? K isn't changing with respect to time, so that becomes k integral from 0 to infinity f of t e to the minus st dt. This here is the definition of f of s, so that just becomes k times f of s. So if you multiply a time domain function by a constant, it's the same thing as multiplying by that exact same constant in the Laplace domain. If you recall when we did whiteboard and we went over here, notice I multiplied by 1/5 there, right? And all I did in the Laplace domain to convert to the time domain, I just multiplied by that same number, that same 1/5 value. So it became 1/5 multiplication there. Okay, so that's the only property that's not specified, but that's a pretty basic one. So Yeah, works really, really well for us. All right, so we did a partial fraction expansion, sort of the brute force way. Now what we're gonna do is we're gonna do, hopefully, a little bit more strategic and more consistent instead of doing it the other way. So when we talked about partial fraction expansion, S plus A, S plus B, S plus C, and we'll call this D. Normally what you had to do was A over S plus little a, B over S plus little b, and capital C over S plus C. And the way that you solve for those coefficients is you put them back under a common denominator, and then you have A times S squared plus whatever, and B times S squared plus whatever, and C times S squared whatever. But there was a lot of math, right? To go ahead and align those coefficients. We're not going to do that. We're going to come up with a different approach that is a much more efficient approach than solving for it. It takes a lot of time when you're learning how to do it. You just takes, it's a process to understand. But once you understand how the process works, you can do them extremely quickly. You can kind of skip a lot of the housekeeping that we need to do. So we'll start off with a generic function. We have an f of s, which has a numerator and a denominator, and both of those are functions of s. So it's n of s and d of s. N is the numerator, d is the denominator. We also require the order of the numerator to be less than the order of the denominator. Does anybody know what I mean by order? It's just the highest order s term. So if you have s to the fifth plus x squared plus 7 over s to the ninth plus 2s plus 5, then the order of the numerator was 5 and the order of the denominator is 7. That's the highest order s term that we have. So essentially what I'm saying is you should never have the highest order terms like that, s cubed over s squared, nor should you ever have something like this. Real world systems, you should never have that. A real world system would always have the order of the denominator will always be at least 1 or greater than the order of the numerator. If they are the same, we can't do partial fraction expansion the same way. We have to do a slightly different approach. And that different approach is we'd actually have to do essentially long division. So here's our partial fraction definition, right? This should be B. Let me fix that. I added a bunch of material in so you can see it. I haven't proofed these enough. Come on. There you go. So we take A over S plus alpha 1 plus B over S plus alpha 2 plus dot, dot, dot. The number of expressions you have over here is based on the order of the denominator. So if the order of the denominator is s cubed, which means the order is 3, you'd have 1, 2, 3 partial fraction expansion terms. All right. If it's 4, you have 4. If it's 50, you have 50 and go from there. The other thing too is, if you notice, I multiplied all those functions out. So though, I mean, the expressions in the denominator out. So each one of these lives in the denominator. So what you're doing is you're just solving for the roots. Does everybody know what the root is of a function? It's when you plug in the root to the expression, the term evaluates to 0. So if I plug in minus alpha 1, right, then that is the root of that. So technically alpha 1 and alpha 2 are the roots, because when you plug in the negative, actually it's negative alpha 1. See, I got typos in here. It should be negative alpha 1 and negative alpha 2. Oops. So negative alpha 1 and negative alpha 2. Oop. Are the roots of the denominator. There we go. Save that again. Bring it back up. If it wakes up. Okay. So for however, whatever the order is, you have the roots. Everybody know how to solve for roots? I'll show you in MATLAB. It's very easy. And your calculators can do it, I believe, too. So let's say I have an expression. Where's whiteboard? If I have an expression, s to the fourth plus 7s cubed plus 5s squared plus 3s plus 1. I need to solve for the roots of that. If it's a second order system, right, you can use the quadratic equation to solve for that, right? Negative b plus or minus the square root of b squared minus 4ac all over 2a. A fourth order one is harder. So in MATLAB, you type in roots of, and then you put in a matrix with a coefficient. That has a coefficient of 1, right? S to the fourth is 1 s to the fourth. So that's 1, 7, 5, 3, and 1. That's how you would put that in. So I'll go back to MATLAB and I'll type in roots of 1, 7, 5, 3, 1. And MATLAB, if I have the syntax correct, will give me what the 4 roots will be. And you know there has to be 4 roots because it's s to the fourth power. If you have a TI-89, I believe you can use fsolve to solve for that. I don't know about the 36s. I would imagine you can do root solving. Let's see. Right, everybody uses a 36 here? No, yes? So let's take a look. Is it a TI-36 or 36X Pro? Finding the roots on a TI, blah, blah, blah. It looks like here you go. No, I don't want that. Here, second and third degree polynomial. So I guess if you watch this,
Are you guys here for the halftime show?
I guess we have to skip the video, but I won't bother doing it here. But it appears that you can use the TI to go ahead and solve for the roots of a polynomial, not for a number, okay? So in MATLAB, it's built in, right? You just solve for roots, and you can see the roots here are complex. Why are they complex? Because I have j terms here. I have plus and minus j terms. So I have 4 roots. 2 of them are real and 2 of them are complex. So you need to trash that. You need to be able to solve for the roots of your functions, okay? That's one of the key things to be able to do partial fraction expansion. But the nice thing is that s plus alpha 1 looks awfully similar to one of the items in the Laplace table. Remember the e to the minus alpha t? That already looks like the table. So doing partial fraction expansion makes it look really closely to the table. All right, I think I'm out of time. We'll pick up with this one on Thursday. Any questions? We already went through homework questions. You get a lab this week with Mark. Hopefully he's already posted it. No? Yes?
Can you do, the MATLAB?
Sure. So the question is, how do you put roots in there? So I just typed in roots and then I use open parentheses because that's a function call. Then I use brackets because the brackets are going to be a matrix with the coefficients. So this was s to the fourth plus 7s cubed plus 5s squared plus 3s plus 1. So the numbers that are inside your brackets, those are the coefficients of the polynomial you're trying to solve the roots for. That's all it is. And because I passed it the numbers inside the brackets, I don't have to define it that way. I'm sure the TI-36X Pro, fancy, can actually solve for the roots as well, but in MATLAB, it's a piece of cake. Okay. Any other questions? Because we're a minute over. See if anybody's got questions. Okay. All right. That's all I had for questions. Thanks, everybody. Have a wonderful day. Don't forget about power on campus if you're here from 4 to 5 in the Hill Auditorium. Have a great day, everyone.
Thank you, Paul.
Thank you.